This is our presentation for ME297 final project. We built a vehicle detector. We're Team YOLO, also known as You Only Look Once. Our team members comprise of myself, Sergio, Mingja, and Rafael. How would you know it's safe to cross the road? Would you use your hearing, your eyes? That's essentially what we're trying to we developed a program to address this problem. Our project revolved around developing the perception component for a fictitious system that would cross one side of San Fernando to another on 7th and 9th Streets. Our project is really what it is devoted to empowering said system to make the decision with confidence, to recognize cars, if the car is on the road or if it's not. Here's an image of the hypothetical route that our system would take. Again, it would be from point A to point B. It would be from off campus to on campus, and it can make the decision either at 7th or at 9th Street. What we did was we trained our system on approximately 500 images from San Fernando 9th and 7th and 9th. Once we collect those images, which we collected on our personal phones, we then split up the data into the three buckets for testing, training, and validation. And again, the main motivation for splitting the data is to prevent overfitting, which was emphasized in lectures. However, we couldn't use all of the images because they wouldn't, the feature extractor didn't recognize some of them, and that'll be touched a bit upon later in the presentation. For our approach, we decided to go with a convolutional neural network. The motivation behind this being that it is known to be optimal for image classification. The general flow of a CNN consists of a convolution layer, a pooling layer, and then a fully connected layer, which is used to connect the neurons from two different layers. In this case, it's a flattened layer, and then finally an output layer that has the portion on classifying the object itself. For our particular experiment, we tested out three different CNN architectures. Model 1 consisted of one convolutional layer with the rest of it being the same. Model 2 consisted of two convolutional layers. Model 3 consisted of three convolutional layers. And right there on the right-hand side, you can see a illustration of what this may look like. And finally, we also decided on two separate optimizers, the Atom optimizer and the RMS prop.
As mentioned earlier in the presentation before, we encountered a huge technical challenge. So when we first imported the data for the model train and during the testing, the model predicted all the images the same results, whether there's car or there's no car. So it's clearly showing that the model is failed to detect the images, which is in our case is the vehicle. And the cause of that is the size of the vehicle inside the image is too small. There are two solutions to solve this issue. One is to recollect data, the other one is to resize the original data we have. Since it's the pandemic, every group member is taking the class online. It is very inconvenient for us to gather again to recollect the data. So the team decided to resize the original data by cropping all the images within the original data. As shown on the right side, by doing that, the vehicle inside the image is enlarged, so it's easier for the model to train. And so with the modified data we use, the model is successfully to predict the images in the testing. And as you can see on the left is the results for South San Fernando and the 7th Street, and on the right is the South San Fernando and 9th Street. And when there is vehicle in the in the image, it will shows up as do not cross, and if there's no car, no vehicle, it shows up as safe to cross. So we collect the time elapsed and the accuracy in the testing and plot it against the three different models with two different optimizer into two bar charts. And based on the two bar charts, it's clearly showing that on the left bar chart, the atom optimizer is taking actually less time elapsed during training, and on the right side you can see the atom optimizer has the higher accuracy in testing. So based on that, we can conclude that the best model we get is model 3, which is the model has 3 CNN layers with atom optimizer.
So there's a huge drive currently and a big desire to do research on object recognition. Two of the research papers that we looked into for this project was one done by the Northeast Normal University in China, and they used the cascade mask RCNN method to detect an object based on the text on that object. This can be seen on the image on the left. So this code or this model was implemented into a small robot that would act as a house assistant. The user would command the robot to grab an item for them, and the robot would use the text recognition to detect that object. Because most of the products have a lot of text that aren't helpful into recognizing them, like for example the Tango waffle, the word Tango is not really helpful in identifying the waffle box. So the researchers added a filter that would filter out these useless text so that only the useful text could be recognized. And once the model was tested, 44 out of 45 items were successfully detected. On the right is an image from one of the researchers in Bulgaria, which compared the YOLO V3 and the single shot multi-box detector or SSD architectures for identifying objects in a video stream. For the both architectures were capable of detecting a human face, but when multiple objects were presented into the stream, the YOLO V3 architecture was better suited for recognizing different objects simultaneously. The focus of this research was to develop an assistance robot for the elderly, and by being able to recognize objects, robots can assist the older folks to get a hold of things. Both of these examples show the importance and the broader impact of object recognition in the real world and the practical applications. The methods presented by the research papers can also be used in our project, as being able to recognize a text on street signs can be very helpful for our delivery system. And so is the capability of recognizing humans and other factors that come into play when crossing the street in a video stream. Thank you.